So we are embarking on our second video with respect to understanding biological membranes, and I'm going to pick it up where I left in the last video when I was talking about the different phases the membrane can undertake. And we're going to review how temperature goes into that and what is transition temperature. We're going to discuss what cholesterol has to do with everything and what sort of motions can we expect from our lipids and proteins in our bilayer. So let's get started. And I just want to start it off with the idea of transition temperature. And really, I want to make sure that you know that when I'm talking about phases of the membrane, I really mean also the fluidity of the membrane. And if you think about it, if you see a question in the test about the fluidity of the membrane, really they mean about the two states, the gel state and the liquid state. And we need to understand that other than the length of fatty acid chains and the level of saturation that I mentioned in the last video, temperature also comes into play. And how is that? Well, we can assume, just like we have that notion that in everyday life, if I heat something up, it turns into a liquid. And when I cool something down, it turns into a gel, or rather into a liquid. So we can just construct an imaginary scale, and I'm just going to put it further in the center. We can just construct an imaginary scale of temperature and say, let's just imagine that at this high temperature, I can experience the liquid state. And below it, below this temperature, I can expect the gel phase. And I can just take this line and say, hey, this is the state in which once crossed up or crossed down, the phase may change. And I'm going to call that the transition temperature. Very good. And if we want to understand, you know what, I'm just going to quiz you now. And I'm going to say that I'm going to have a statement here, increasing an alien green, increasing the level of saturation. Saturation may have the same effect as blank, the temperature of the membrane. And what I urge you to do is to pause this video and try and fill in this blank. So pause it now if you want to work on it yourselves. Very good. So what I'm going to do here is, first of all, I'm going to look into what do I mean by increasing the level of saturation. Well, let's just say this is my molecule, and those molecules have straight, I'm just going to draw it in a different way. Those molecules all have one kink here. This guy has one kink this way. This guy has one kink this way. Perfect. So increasing the level of saturation means I'm going to have more saturated bonds, meaning I'm going to have more single bonds and less double bonds. And this is saturated, just so you would know. If I have this chain, it is a saturated chain. And if I have this chain, it is a non-saturated chain. So by increasing the saturation, effectively, I'm just increasing the number of single bonds. So I'm going to do just that. I'm going to make all of them single bonds. I'm increasing the level of saturation. I'm saturating my molecules. And this is going to cause stronger interactions and a gel phase, and a more gel phase. Okay, so increasing the level of saturation, let's just write here, and I do write on my exams, I do correct statements sometimes to make it easier on me. Increasing the level of saturation may have the same effect as, let's see, in order to get the same effect, I need to decrease the temperature. So decreasing. Let's read this again. Increasing the level of saturation, causing more single bonds, may have the same effect as decreasing the temperature of the membrane. Good. All right, so having understood that, let's move on and discuss cholesterol. And it is not very important to know what cholesterol is. It's not important to know that it's an organic steroid alcohol, but you can just take it as is and say, oh, it's a something, or you can say, okay, it is a steroid. but it doesn't really matter. I'm not here to discuss chemistry. Chemistry is not my favorite anyways. So what we're going to do here is we're going to discuss how this guy affects its environment. Very good. So let's see what's going on. I'm just going to write here, below transition temperature, noted by temperature of membrane, transition temperature of membrane, and above transition temperature of the membrane. Very good. And we're just going to start throwing these terms that you may encounter in your exams. Sometimes I like to keep things simple, but sometimes I like to use the same expressions the departments use. So let's see. Below the transition temperature, that means, let's go up and see, that means that below the transition temperature, that means a gel state. So we're looking at a gel state. Below the transition temperature, I know these guys are packed very closely together. We're in a gel state. These guys are going to be very closely packed. So these guys are going to be very, very closely packed. This cholesterol in between them is going to spread out and say, hey, no more. Get away from me. You're getting too tight. I need some air. I need some distance. So below the transition temperature, what is the cholesterol going to do to the fluidity? Well, these guys want to get closer because it's below the transition temperature, and cholesterol is pushing them away, making things more fluid. So below the transition temperature, cholesterol increases fluidity. Let's see what happens on the flip side. Let's take a classic case in which this guy here says, hey, I don't like this guy. I don't like the other molecule. Gives me attitude. I'm just going to go away. And this guy says, hey, you know what, guy? Up yours. I don't like you anyways. And he's going to go away. And cholesterol is smack down in the middle of them. So cholesterol is going to reach out, grab them both, and say, you guys are not going too far apart. Stick around. Stick around. So what it's essentially saying is that when we're above the transition temperature, meaning that we're in a very liquid state, these amphihepatic phospholipids wants to break apart. They want to break apart. The cholesterol brings them together. Decreasing the fluidity. So above transition temperature, cholesterol decreases the fluidity. And you would have to excuse me for using these terms, transition temperature, but these are just terms that are good to work with when you're studying for an exam, and this is what we are here for. Perfect. And being that we can make it a little bit more difficult, as it is in the minimals, they use viscosity. So let's see what viscosity comes into play. Does cholesterol increase viscosity below and above the temperature, or does it decrease? So let's consider. If we have, no, that's not it. If we have viscosity, and viscosity goes up, we're looking at a more gel state. And as viscosity goes down, we're looking at a more liquid state. Or decreasing, this is decreasing the fluidity, this is increasing the fluidity. These are just things that you need to kind of understand. So let's just see. Below the transition temperature, cholesterol increases fluidity. It increases fluidity, so things are going to be less viscous, so it decreases the viscosity. And when above transition temperature, cholesterol decreases the fluidity. Things are less fluid, they're more gel, so the viscosity is increased. Cholesterol increases viscosity. And if you read this, you go ahead and you read the minimal requirement question about what cholesterol does for different phases, and you will understand. Perfect. We're going to go ahead and we're going to talk about possible motions of membranes and lipids and proteins, of membrane lipid and proteins. And before we do that, I just would like to introduce the possible proteins that we may have in our layer. So I'm just going to draw our layer here. This is our lipid bilayer. Very good. We have the heads here. These are the heads right here. Very good. So we may have proteins that are just on the outside part, These are called peripheral proteins. And we may have proteins that span the length of the bilayer. They span the length of the bilayer. They are embedded in it, and they poke out both on the inside, both on the outside. They kind of poke out on both sides, and these are integral proteins. Perfect. These are integral proteins. And if you're wondering, hey, what is this weird antenna looking thing? Well, this antenna looking thing is a carbohydrate. Don't worry about that. That does not really concern us at the moment. And we're wondering, how can these guys move around? How can these guys move around? So let's take a look at the lipids. And these are just the main motions that the lipids can undergo. Let's just say I'm looking at this lipid molecule here. Let's switch the color. I don't like this color. It's too inconspicuous. Let's take this lipid here, where there's a few things it can do. It can move around in the layer. Let's just say it moves over there. It can just, this is called lateral diffusion. It can rotate around. This is called rotation. It can also switch places with its teammate here. You can go flip around, and his head is going to move here, and his legs are also going to move. This is called a flip-flop motion. Let me draw just to make sure that you know what I'm talking about. This is this guy, this is his neighbor here, and it just flips around to here. This is basically a flip-flop motion. And there's also a motion where they can just move like so from side to side, kind of like in a rock concert. La da 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 da, there we go. But this motion is it's somewhat of a motion that comes alongside others, so I'm not going to really talk at length about that. So this is what lipids can do. And just so you know about the flip-flop motion, the motion where an outside-facing lipid or an inside-facing lipid is turned to being in the other orientation, the flip-flop. And as you can imagine, this actually requires energy. This actually requires quite a bit of energy. It's not like swimming forward and backwards or rotating. This requires energy, so it's unfavorable. Unfavorable doesn't mean we don't like it. It just means that it requires energy. Very good. And let's take a look at what the proteins, these integral proteins, what can these proteins do? Well, it just so happens that they can also laterally diffuse. And again, I'm going to switch colors because this color is horrible. Again, they can laterally diffuse through the membrane, just move around through the membrane, and they can also rotate. And this is the possible motions we can go through. And in the next video, I'm going to combine the missing slides from the diffusion slide, understanding the different ways of measuring these types of diffusions. And again, I'm hoping my Skype bar is not causing too many troubles. So we are going to meet in the next video and discuss how do we measure the different diffusional methods, or rather diffusions, that these guys can undergo. The lateral diffusion and the rotational diffusion. How do you measure those? See you in the next video.